Thank you, Silvia. Thank you, Daniel, for the invitation. I'm going to do a talk a little bit more presenting how we came up with the ideas for this project. And I will invite you to contact me or go to the paper if you want to know the details. I'm really glad when people come and ask me, like, hey, can we discuss the paper? I found the talk interesting, but I promise that I won't give proof because I know it has been quite, I mean, people maybe already be a little bit tired, no? So let me try to keep it light. So this is a collaboration with Edgar Pimentel at PUC Rio, and now it's also at Coimbra. And it's actually also happened in a congress like this, a big congress. So before the pandemic, so when we have the opportunity to interact with each other. And this is something that I love, you know, and I'm missing a lot. So again, I also use this as a hook to tell people, like, please come and contact me because I'm feeling kind of disconnected with these online presentations. So without further ado, let me tell you about the nature of the equations that I want to present now. They look a little bit arbitrary, but there is a reason for this. So we're looking at the minimum of the Laplacian or minus the Laplacian and the gradient of u minus 1 equal to 0. These give me three pieces of information, no? So on the first hand, each one of these factors, the Laplacian and the gradient minus 1 have to have a sign, no? So I know that my solution is superharmonic, the gradient is larger than 1, and besides that, I know that if the gradient is strictly larger than 1, then my function is harmonic. So this should remind you the obstacle problem. So the obstacle problem tells you the following information. You have a superharmonic function that is above an obstacle C, yeah? And whenever the function u is separated, there is a mistake here already. If it's strictly larger than the obstacle, then the function is harmonic. So this is the picture that we keep in mind. There is an obstacle and u is like a membrane that we try to adjust on top of the obstacle, no? And this picture is sponsored by the book of Petrosian, Shagolian, and Uralsova, no? Very nice book on obstacle type problems. Other way that we can understand this problem is kind of a very degenerate type of equation. Why degenerate? Because the ellipticity doesn't hold everywhere. It only holds on the region where the norm of the gradient is strictly larger than 1, no? And in the other region, we lose the ellipticity. So this has been studied before. In 2013, Imbert and Luis Silvestre studied estimates on Holder estimates or the Krylov-Safanov theory for equations that hold only when the gradient is large. And they were able to show that the solutions are locally Holder continuous. So this is a type of equation. Here we are solving the Laplace equation only when the gradient is larger than 1. Yeah. So already we know that for this model, solutions are going to be Holder continuous. So in our work with Edgar, we are bound to say a little bit more than that. Other place where this type of equation have been studied before is a paper of Evans in the 70s, 79, and is a little bit different, no? And we will notice what a big difference makes to change this minimum by a maximum, no? So the problem of Evans, instead of having the minimum, he has the maximum, no? So it tells you a different piece of information, no? Solutions are subharmonic, the gradient is always smaller than 1, yeah? And whenever you're separated, again, this is a strict inequality, whenever you're separated from the obstacle, from the restriction, then you're harmonic. But this already tells me that the solutions are automatically ellipses. So these are more regular. Actually, Evans gets to show that solutions are almost C2, no? They're C11. So there seems that there is a gap on regularity by just changing the maximum with the minimum. Another important paper that is going to appear later on in in one of our jobs, works with Arturo, is the following one, where they interpret the problem. Well, this was actually before Evans, no, but is a problem that came from Evans, from obstacle problem type perspective, no? So they say that the problem of the maximum is equivalent to an obstacle problem where the obstacle is the solution for the Icona equation. Yeah, so this already connects the actual obstacle problem, classical value obstacle problem, with these gradient constraints. So let me tell you how we can think in physical terms about this problem. And it's kind of a very relaxed motivation, no? So it's a cartoonish motivation. So let's think about two players, and they are trying to control a spaceship. So Rick and Morty, they are inside of a domain, and they have different goals. No, Rick is an adventure type, and he wants to explore Omega as much as possible. And Morty, he's very scared, very precautious, and he wants to leave Omega because it's very dangerous as fast as possible. So these two players take turns and decide the following. So the first player, Rick, decides if the ship drifts with Brownian motion, so the drunken walk, or he just gives control to the second player, Morty, which is going to move in a given direction. So this is the decision of the second player at maximum speed. And let's say that the speed is equal to 1, no? So the problem is, can we compute optimal strategies for these players? So what they should do to maximize their preferable outcome. So let's think about the strategy. The strategy tells me the following. So you have the domain, and inside the domain, the first player is going to decide where the motion is going to follow the Brownian regime. And on the other part of the domain, or whatever is left to the second player, Morty has to decide the direction, no? The magnitude is already fixed. And see, for example, in this configuration, in this picture, if you start at this point, then you follow the flow. Perhaps you may enter the Brownian motion and you don't know what is going to happen. No? You know the probabilities. It may get outside, it may enter again, and so on. And eventually, it may exit the domain. Yeah. So this is a random problem. And the optimal time is also going to be a random variable. So what we want to do, or the value of this problem is given in terms of an expected value. No? So we define u of x as the exit time from Omega starting at x, and then take the expectation. So the first player wants to maximize this time, and the second player wants to minimize it. Okay? And this is going to lead us to okay, so let's make it a little bit interactive. So here we have this configuration, and I'm going to ask you if you want to answer me on the chat or whatever, make a reaction, I'll be happy to see it. So the question is the following. You start at this point, this is Omega, this is the complement. What should the first player choose? Brownian or Icona? So let's say that Brownian you say yes, and Icona you say no. So you think about it, and you figure out that if I choose Brownian, there is a good chance that I get away from the complement, which is what the first player wants to do. No? So actually, when you're close to a boundary that seems very concave, yeah, it is preferable to choose Brownian. Okay, because it gets you away from the boundary with a good probability. This is heuristic, but it helps us to get a feeling of how the solutions or how the problems is going to look. On the other hand, if the region looks very convex, very thin, no? When you choose Brownian, you're going to get, with a good probability, closer to the boundary. And keep in mind that Brownian motion is faster than deterministic motion, no? than Icona, because Brownian motion is going to lead you to instantaneous rate of propagation. No? So the speed of Brownian motion in a small interval of time is kind of proportional to the square root of dt. Meanwhile, the Iconal motion is going to, the Iconal regime is going to give you proportional to dt. No? So in this situation, it's quite the opposite. you should Rick, the first player, should choose the Icona regime. And in a moment, I'm going to discuss solutions and see what happens. So before that, let's see how the dynamic programming principle leads us to our equation. So let's remember that U is the expected value of the, in this case, for the optimal strategies, is the optimal time for the expected value for the time, no? So Riggs, which is the first player, knows what Morty, if he chooses the optimal strategy, how it's going to affect to the function U. So here in the dynamic programming principle, we are assuming that we know U perhaps in a neighborhood of X, and let's run the game for a tiny amount of time dt, no? And then he looks at the possible two outcomes. If he chooses a Brownian, so the value of U is going to be changed by this quantity, yeah? And if he chooses a Icona, yeah, he knows that Morty will try to minimize this quantity, and this is how the value of U is going to actualize, no? And keeping this in mind, what he wants to do is to take the largest one, because he wants to maximize the time. And then, as is a standard now, you subtract U of X on both sides, divide by dt, send dt to 0, and the equation that you get is the following, no? So here, so you get 0 equal to, well, the generator of the Brownian motion is half the Laplacian. So we have this term here. 1 appears because we have this dt over here. I'm actually, there is a minus sign that I'm taking outside, so the maximum becomes into a minimum, no? And here what we are doing is the minimum of U is minus the gradient, no? By choosing the best direction for Morty. So we get this type of equation, which is essentially the one I presented before, with the difference that, well, instead of 1/2, we have here 1, and here we don't have a right-hand side for the Laplacian, but after a appropriate change of coordinate, we may see that there are the same technicalities in both type of equation, okay? So finally, 2 comments. This is also kind of the expected theory that you will get from optimal control, is that once you solve the Hamilton-Jacobi equation, you know the strategies. This is why the value function is important, no? Because you already splits the domain into regimes, no? The regime where the gradient is strictly larger than 1, that means this is the Brownian region, and the region where the gradient is exactly 1, no? Where the number of the gradient is exactly 1, which is the Icona region. And in that region, Morty, the second player, just have to follow, you have to descend the gradient of it. Okay? So we came again to the same problem, no? This is the problem that will appear, no? If you allow, if you do a small modification, no? You say that you don't pay anything for being in the Brownian region. So you don't count the time that you are in the Brownian region. So that's exactly the problem that you will get. Okay. So as I said before, this can be interpreted as an obstacle type of problem. There is a non-variational theory that we can apply, the theory of viscosity solution, and we can construct solutions using the Perron method. And we can actually also show the comparison principle, uniqueness, etc. No? So in this case, we can construct the solution as the least superharmonic envelope or super solution envelope of the zero function. Yeah, which is the zero function is automatically a sub-solution of this equation. Okay, so let's see what kind of solution may appear. Remember that I said that if the point is close to a region of the domain that looks convex, the best strategy is to choose Icona. Actually, if the whole region is convex, or even a little bit weaker than that, if the mean curvature is not negative, then the solutions to these problems are going to be the distance function, not the solution of the Icona equation. And this already tells me something very interesting. The solutions of the iconal equation, the distance function, are not better than Lipschitz. Yeah. So this brings a distinction with the problem of Evans, where the solutions were almost C2, the solutions were C11. In our case, we cannot hope that the solutions are better than Lipschitz. Okay? And this is actually our result. With Edgar, we show the solutions of this obstacle type problem are Lipschitz continuous. Moreover, and this is quite the technical, or I would say the most interesting part of the paper for us, is to show that even though the gradient of u may be discontinuous, the norm of the gradient of u is a continuous function. So this tells you something about the free boundary condition. As you approach the interface that separates the Brownian regime from the Iconic regime, the gradient of u approaches 1 in norm. So what's the idea of the proof? So we use a diminution oscillation. No? If you want to show that a modulus of continuity, and you have an equation that is a scaling variable, you may try to show a diminution oscillation to this function. So the gradient of u truncated by a level lambda, no? And this is a function that is subharmonic. So you already have some type of mean value estimates. So you consider, forget about this, this is a typo. So you consider two alternatives, no? Either the function v, which is like the gradient, is above 1 most of the time in the ball of radius 1, or is below 1 sometime in the ball of radius 1, okay? If the first alternative holds, where the eta is a constant that I can conveniently show at the end of the proof, no, at some point, then you get to show that u, the original function, not the gradient, is flat in a ball of radius mu, where mu is another radius that I conveniently show. So here we are saying that my solution is very, very close to be an affine function. Yeah, and here I can use the theory of higher regularity by approximation of Ovidiu-Sabin, which is also inspired by Luis Caffarelli in the 90s, to show that u actually becomes C1 alpha. Yeah, you get a lot of regularity from this. You are saying that u is a perturbation of a linear function. Yeah. Otherwise, you get to say, well, v is less than 1 sometime, and because v is subharmonic, you can use just the mean value formula and say that you diminish the oscillation from above. Yeah. And this is, so when you iterate either one of these two alternatives, in the worst case, you are always diminishing the oscillation from above, so you get to show a Holder modulus of continuity. So there is an open problem, no? We were able to say something about the regularity of the solution, but we know nothing about the regularity of the free boundary. This is something that I would like to invite you to think about. And here is an idea. Actually, what we exploited at this part of the presentation, at this part of the work, is the non-variational structure of the equation. But this equation should also have a variational formulation, which is to minimize the Dirichlet energy with that constraint. Yeah. So are these two problems equivalent? Is the potential theory formulation equivalent to the viscosity solution formulation? I thought for a while that this problem was actually easy, but it's not. Yeah. And notice that this, even though the functional is convex, is our favorite functional Dirichlet energy, the constraint is very non-convex. Yeah. So that's a problem. Okay, so now let me go to serious issues, to serious models, and discuss a problem in race theory. You already talk about something that it was kind of cartoonish, and there is a real life problem. So in race theory, we have the following problem in an insurance, that the value, the money that you have in the insurance, well, it was proposed by Lumber, Kramer, and Finetti, is given by the following formula. No? So it's an initial amount of money. Then there is the contribution of the people that is in search, no? And then you have the jumps, the claims that come to the research with some random distribution. No? So the problem is that with this capital, you're going to start paying to the shareholders, and you want to maximize the money that you give to the shareholders up to the time of ruin. No? So what's the best strategy? How do you pay them according to the amount of money that you have? So this is a problem that has been well studied since long ago. And what we're trying to do now is to understand what happens when you have multiple insurrections. So the multiple dimensional problem is not so well known. So as before, we have a problem of maximizing the expected dividends up to the time of ruin, which in the case of any search looks something like this. And then you, the value function, also satisfy a dynamical programming principle and a Hamilton-Jacobi equation. Yeah. So dynamical programming principle you can deduce as before, no? So you may consider L, the amount of money that you're going to pay in an instant of time from t to t plus dt. No? So U is going to actualize in this fashion, and then this is the money that the shareholders receive. No? When you take the limit when dt goes to 0, you get this type of equation where scripted L is the generator of the non-local process. It's usually an operator of an integral differential nature. No? And this term over here is very interesting. No? So, well, you can do the computation and you're going to see that this is either plus infinity or 0. It's plus infinity if the components of the gradients are at least one of them less than 1. Yeah? And 0 else. So this is actually a constraint. No? This is telling you that the components of the gradient of U have to be bigger or equal than 0. Okay? This problem is overdetermined. What we can do is a relaxation, and this was proposed by Asquith, Mueller, and Palmowski. And they look instead at the following problem. No? Instead of looking at the problem LV equals 0 and this constraint, you say, well, I'm going to take the least super solution of this operator that satisfies the constraint. So an obstacle type of problem. We know very little, I would say, about the regularity of the solution for these problems. Yeah. So another open problem: change your diffusion by the best friend, the Laplacian, and can we say that the solutions are Lipschitz discontinuous? This is much more delicate than the previous one. Okay. And let me mention what is the heuristic, what this should be true in dimension 2, and I won't bet money that this is true in dimension higher than 2. In dimension 2, outside of the Brownian region, we should have that U is one-dimensional, yeah, because either one of these is equal to 1, and it's superharmonic. So a one-dimensional function that is superharmonic or concave is automatically Lipschitz. Yeah. So the problem is that this is very heuristic, and we don't know how to make this idea to work across the regions. No, we can say this in the interior of each one of the regions, but we don't know how to connect this across. Okay. The other problem is if you look at the real life application. So if you look at the non-local problem, what's the regularity of the solution? Yeah. To finish, I would like to mention some very recent work, ongoing work with a student, Arturo. He's going from Guanajuato, now he's going to McGill. And we look at the following discretization. No? So we fix the strategy for the first player, no? for the Brownian. So we fix the Brownian region, and we assume a lot of regularity. So let's say after a change of coordinate, the Brownian region, the interface that separates the Brownian region from the conal is just flat. Okay, so it's clear what we have to solve numerically to find solutions of this problem with this strategy. So in the conal region, you solve the conal equation, which has this presentation, this discretization, and the Brownian region, you solve this one. No, what you do on the interface is actually to solve the conal equation. Yeah. And this gives you the optimal value for the discrete problem. So this is something that we were able to implement, and the solutions look quite nice. No? So on the corner region, they look like distance functions. He implemented the distra and fast marching method. And on the Brownian region, well, you implement your favorite solver, no? But now the question is, do we know if these solutions converge to the actual viscosity solutions as the discretization goes to 0? And I thought it was easy, and it was not. This is quite delicate. And the problem is that there is no uniqueness. Or we don't know. I'm sorry. The uniqueness is not obvious. That's the issue, no? This is a Hamilton-Jacobi equation with discontinuous coefficients. And we know that the discontinuous coefficient for Hamilton-Jacobi give a lot of problem for proving the comparison principle. So we can actually show that there is uniqueness, but we cannot show the comparison principle. And this is in the paper of Evans that I was discussing before. Here, the conditions on the interface should be interpreted in the viscosity sense, no? And they are telling you a very weak version of what should be the interface condition, no? So the idea is that you add a small viscosity, vanishing viscosity, and then use the Bernstein method to show that the solutions are actually semi-concave. And under semi-concavity, you have enough regularity to apply comparison principle. So that's how you show uniqueness of solutions. So here is a problem, no? As in Bresis and Siboni, we would like to know if there is a classical obstacle problem interpretation of this problem. And this is what we conjecture should be true. You solve the eikonal equation on the eikonal region and leave free whatever happens on the interface, on gamma. And then with that obstacle, you find the solution of the obstacle problem. So this is a type of Signorini or fine obstacle type of problem, okay? So is this the same as our previous model? The numerics suggest that this is true, but then there is a mathematics that we don't know. And that's it. Thank you very much.